speaker is Shubham Gupta. He is from HRI Allahabad. Oh, sorry, it is in Prayagraj. So he is speaking about the D of -1 occurs in imaginary quadratic fields. So Shubham, you can start.
Okay, sir. So, thank you, sir, for giving this opportunity. Good evening, everyone. My topic is D-1 tuples in imaginary quadratic field. The following is the content of my talk. First, we will see the definition of M tuples, then some examples and some results related to this. After that, we generalize our definition, and then we will state our main theorem. And the following these steps, like upper bound of D and lower bound of D, we will prove our main theorem. So let us start with definition. A set of m positive integers is called a M tuple with the property Dn. If we take any to a distinct element from the set, multiply them and add plus n, then it will become a square in Z. For example, consider a set 1 to 5. You can take any to a distinct element, say 1 and 2. So now one can see that 1 into 2 minus 1 is equal to a square of 1, means which is a square. And similarly for the other tuples. So this set is a Diophantine 3 tuple with the property D minus 1. So Diophantine found a set of 4 rationals satisfying the above property for n is equal to 1. The first Diophantine 4 tuple was found by Fermat. And Becker and Davenport proved that this particular quadruple cannot be extended to 5 tuple with the property D1. In 2004, Andis Joella proved the non-existence of 6 tuple with the property D1, and further he also showed that there exists at most finitely many 5 tuple with the property D1. And 2019, Bohe et al. Proved the non-existence of 5 tuple with the property D1. So similarly, we have many results for M tuple with the property D minus 1. So here we consider a D minus 1 property. So in 2005, Joella and Proust proved the non-existence of 5 tuple with the property D minus 1. And recently, Bonne-Coyquet et al. Proved the non-existence of 4 tuple with the property D minus 1. Okay. So now let us generalize our definition from positive integers to any commutative ring with unity. So a set which is a subset of R minus 0 is called the M tuple in R with the property Dn. So means if we take any to a distinct element from this set, multiply them and add plus n, then it will become a square in R. So one can easily see that 1 to 5 minus 24 is a Diophantine 4 tuple in Zi. Here, keeping this in mind, that in Zi with the property D minus 1. Okay, so let K be an imaginary quadratic field, OK be its ring of integers. In 2019, Adjaga showed the non-existence of M tuple in OK with the property D1 for M greater or equal to 42. So the natural question one can ask that, can we generalize this theorem? So we answered this question for n is equal to minus 1. So in this talk, we will prove that if m is strictly greater than 36, then there doesn't exist Diophantine M tuple in OK with the property D minus 1. So in this talk, we will prove this theorem. Okay. So actually, we will prove our theorem via contradiction argument. So suppose we have a M tuple in OK with the property D minus 1 such that m greater or equal to 37. So we will follow these steps to proving our main theorem. Let we have a triple ABC in OK with the property D minus 1. And there exists a D belongs to OK such that ABCD makes a quadruple. Then via some calculation, we can get a system of Pelian equation. And we use this solution of this Pelian equation and a result of Jetty-Chevik and Ziegler, we can get an upper bound of D. And for getting a lower bound of D, we use a regularity condition on quadruple ABCD. So after combining the these lower bound and upper bound of D, we can get a desired contradiction. So we will follow these steps. Okay. So let us fix some notations. K be an imaginary quartic field, OK be its ring of integer. Alpha belongs to OK, and we define norm of alpha is equal to alpha into alpha conjugate, and the absolute value of alpha is equal to root of norm alpha. So in this talk, if we say ABC is a triple, it means that it is a three tuple. It is a three tuple in OK with the property B minus 1 satisfying this condition. And for similarly for other triples. So and last, if ABC are triple, so by definition there exists RST belongs to OK satisfying this condition. Actually, this thing is coming from definition. So RS and T so will hold. Okay. So let ABC be a triple. If there exists a D such that ABCD makes a quadruple, then via definition, we can get these equations. So the extracting the value of D from this equation and put it in the remaining equation, we can get the system of simultaneous Pell's equation. So here we can get, okay. So now we determine the upper bound of D. So in 1998, Bennett proved a theorem which is related to simultaneous approximation of Fresnel. And then analogously, Yarty-Chevik and Ziegler proved the following theorem. Let theta is equal to root over 1 plus ai by t, where I is equal to 1 and 2. A1 and A2 are distinct algebraic integers, t any algebraic integer, and let M, T, A0 and L defined are taken like this thing. Then for all algebraic integers P1, P2 and Q belongs to K, we can get this inequality where lambda C1 inverse, L small l capital P small p are like this. So here there's another lemma. Suppose we have an M tuple in OK with the property D minus 1. So for M greater or equal to 4, multiplication of any two distinct element from the set will not be a square in OK. Actually, this lemma can be proved by a straightforward calculation. You can prove this lemma. Here there's another lemma. Let xyz be the solution of the Pellian equation, and our triple ABC satisfying these conditions, like the absolute value of C is strictly greater than 4 times absolute value of B and absolute value of A greater or equal to 2. And we take theta 1 of 1, theta 1 of 2, theta 2 of 1, theta 2 of 2 like this, satisfying these inequality. Then we can get these two inequalities, 2.4 and 2.5. Okay. So further we consider theta 1 is equal to plus minus SYA root A by C, and theta 2 is equal to plus minus T by V root B by C. Okay. Okay. So after some calculation, we can get that theta 1 is equal to this one, and theta 2 is equal to this one. Okay. So after that, we take A1 is equal to minus B, A2 is equal to minus A, T is equal to ABC, and M is equal to capital V. Okay. And then we apply the previous lemma and Yarty-Chevik Ziegler result to get a upper bound of D. So, okay. So let ABCD be a quadruple satisfying this condition. Okay. So satisfying these 4 conditions, then the absolute value of D is strictly less than this quantity. So this theorem gives the upper bound of D in terms of C. Okay. So now our next step is to determine the lower bound of D. So let ABCD, let ABC is said to be regular triple if C is in this condition, like C is equal to A plus B plus minus 2 root AB minus 1. Okay. Let ABCD be a quadruple satisfying this condition. Then at least one of the triple ABC and ABD is not regular. Actually, via contradiction argument, we can prove this lemma. And using this lemma, we can get a lower bound of D in terms of A. So which is given in this theorem. Let ABCD be a quadruple satisfying this condition. Then the absolute value of D is greater or equal to this quantity, like absolute value of a square divided by this one. Okay, so this theorem gives the lower bound of d in terms of a. So till now we have a upper bound of d and a lower bound of d. So now let us start the proof of our main theorem. So via computation, one can check that if suppose we have a quadruple, then the absolute value of d greater or equal to 12, and for a quintuple, absolute value of d greater or equal to 15. Actually, we prove our theorem via contradiction argument. So suppose there exists a m tuple in OK with the property d minus 1 such that m greater or equal to 37. So this implies that a4, a5, a6, a7, this one is a quadruple. So now we get a lower bound of a7 via using the previous theorem, like a lower bound of a7. So from here we can get the lower, so the absolute value of a7 is strictly greater than 35. And now we consider quadruples, this a7, a8, a9, a10, and the second one is a10, a11, a12, a30, and so on up to a19, a20, a21, and a22. Okay, so and we apply the lower bound theorem on these quadruples, so we can get these inequalities. Actually, we apply the lower bound theorem on these quadruples just one by one, so we can get these inequalities. So from here we can get the absolute value of a22 is greater or equal to absolute value of a7 to the power 32 upon 330 upon 65 to the power 31. So from here we can get the lower bound of a22. Okay, so further now we consider quadruple a7, sorry, a4, a7, a22, and a22 plus k for every k greater than 0. And now we apply the upper bound theorem on this quadruple. So from here we can get this inequality, and this holds for every k greater than 0. So if we take k is equal to 15, so from here we can get a upper bound of a37. So so from here we can get that absolute value of a37 is strictly less than this quantity. And now again we so now from here again we apply the lower bound theorem on these quadruples, this one, and now from here we can get these inequalities. So till now we here this inequality and this inequality. So for proving our main theorem, we need to only show that this inequality. So we claim this one, this inequality. Okay. So after simplifying this inequality, we can get the absolute value of a22 is strictly greater than 1.82 10 to the power 7. But we have seen that the absolute value of a7 is strictly greater than 35. We have seen that. So we use this lower bound of a37. So from here we can get the lower bound of a22, which is 10 to the power 27. So from here, so our claim is proved. So finally we can get this inequality, which can one easily seen that this is a contradiction. So hence m greater or equal to 36. So this completes the proof. So thank you for attention.
So is there any question from the seminar hall? So one question.
Shubham, can you hear me?
Okay, sir. Yes, sir.
Yes, don't worry. No, I'm asking that 36 seems to be very, very high. So,
okay, sir. Yes, sir.
Yeah, because you over Q as you over Z, you have seen that 5 tuple is not there. So, is any guess for you? I mean, I know there is no such result exists there in ZI, but what is your guess? Is there any guess?
Actually, sir, I am trying to reduce this bound. Actually,
no, I'm not talking about, but some conjectures. Like...
No, actually, here there is no conjecture as far as I know. But I think M should be strictly less than 5, I think. I think so, but
So you expect whatever happens in Z, the similar thing will happen in ZI?
yes, yes, sir. I am
Did you have any
expecting it.
discussion with Tujela?
No, sir. No, sir. Till
Maybe,
now,
I mean, he was telling me, I don't know, he has submitted something in this, our proceedings on this in ZI about 5 tuples. So you may discuss with him that, what is the guess, because he's the master in this area. And
yes, sir.
talk to him, because 36 is certainly huge. Don't expect
Yes.
anywhere near 10 even. Okay, so yeah, I mean, nice talk, Shubham. Thanks.
Okay, sir. Okay, sir. Thank you, sir.
Catch with Tujela.
And any
Okay,
other
sir.
question? So if there is no other question, online participant, is there any question? It seems like there is no question from online